Welcome to Chapter 9, Subroutine and Control Abstraction. Subroutines and Control Abstraction. In Chapter 8 and Chapter 7, we talk about data structure and composite data type. And in this chapter, we will be focused on the control structure. First, let's talk about functional abstraction. Functional abstraction, it is also known as procedural abstraction. A function performs a specific task, given stated precondition and postconditions. It has a name, a parameter, and a return value. It may be used by name as long as appropriate values or objects are passed to it as parameter. Preconditions are met, and its return value is used in an appropriate context. In this sense, we have abstracted the function and hidden its implementation details. So basically, a function, you have some parameters and some return value. And that function, you have some precondition and then some postcondition. And you met that precondition and provide some condition, provide some result that you met the postcondition. And sometimes there are some side effect that's unexpected by the programmer, but will be produced. And then if something wrong here, you will provide exception. So that's something about function or procedure. So let's look at what are the functions. We have code sections, subroutines, procedures, operations, functions, method, and lambda expression. All of these are related to functions or related to so-called procedures. So all of these can be considered as functions or procedures. Basically, procedure is sometimes we use this term for some function that has no return, while function with return value. A method is used in OOP. And lambda expression is based on lambda calculus and used for functional programming. And code section is early day. You have some code, get started and finish somewhere, and then go to other section. When there is no concept of procedure or functions, subroutine and procedure are close. And actually, these four different names are very close. You may have some subtle difference between them, but sometimes they are used interchangeably. The advantage is modularization, code reusable, packaging, teamwork, abstraction, and reliable. So basically, the functional abstraction is just to provide the interface that you actually call the function by the signature, including the name, return type, and the parameter, and you keep the inside as a black box. So you provide modularization. You can actually call some function and return. Call some function and return. And the code can be reusable, and you package it so that it is put into a certain library or some class, so for other people to use. And then you can break down the whole project into different sub-functions. And that also provides abstraction and readability. Functionality, we have the visibility modifier, scope, and generic, And then we have the function name and parameter list. The whole thing, we call it method signature. And method signature is used for matching the function. So method signature is used to matching the function so that we can decide whether we should call static binding or dynamic binding. That actually depends on the matching of the methods. Topic in this chapter, including the call stack, calling procedure, the epilogue, and the prologue, and then parameter passing, exception handling, and coroutine. So here in this chapter, we talk about the mechanism. We talk about the mechanism, or what we call pragmatics. Remember, our textbook is Programming Language Pragmatics. That is the mechanism that behind functions, also called control structure. So these are the topics we will cover. Basically, we have a function. We enter it, we exit it, we have prologue, we have epilogue, and that's the calling sequence. And then when we get in and get out, there's a stack associated with it. We call it call stack. And then parameter passing is achieved by call stack. And if something wrong, we break out to an exception handling routine and come back. That's the exception. And coroutine is something that you have two functional call. You can switch contact between them, and then, or it can be in different threads, and then you talk to each other. That's some of the feature we have for the functions. Stack layout. First, let's look at the stack. Review of stack layout. Basically, we have static, call, global, unavailable, and explicit constants, and smaller scalar may be stored in the instruction themselves. So basically, we need to know about the stack layout in order to know about our variable, how are they stored. And that's related to memory allocation strategy to maximize the performance for the CPU, and also minimize the memory that being occupied. So for Java, we have this Java class method area, and this is one of the model for the Java memory model. So we have method table, we have field information, we have custom pool, we have class variable, we have type information, method information, and reference to class loaders. And here is Java stack and heap. And these are not in the method area. This is in somewhere else. So our function, we call and push into the stack, and then some of the reference may go to heap to obtain its object. So here's the program, and it got pushed and popped from the stack, and then object can be created into heap and then save the reference to the stack. And we have some of the object reference. It may be stored in the heap, and there is a handle pool and the object pool, and then the class data is actually in the method area. That's the structure for Java memory model. And here is the class method area in stack. And we have different language. We can have the growth of the call stack. We have the C call stack and assembly call stack. So let's look at the assembly call stack. The assembly call stack is in more detail. We have the local storage, save register, save the frame pointers, and then save the link registers, and we have the parameter area. So it's in more details. It is actually push and pop, actually for different registers. and it will be saved into the memory if you actually have the assembly call stack. And this is actually what really is done by the CPU. And then in C language, we actually utilize the assembly call stack and to support C call stack. And C call stack is more conceptual, and assembly call stack is more in details. But this actually is on top of it. And Java code stack is different. Java code stack is on top of the Java virtual machine. So it actually has different structure to C. It may not be the same with the native code C language or assembly code. The native code actually written in C or assembly. And in Java, that's another different level. We map this one onto the implementation languages, for example, C language that's run on a certain machine. Machine code that can be assembly. So review of the stack layout. Basically, we have A function calling B, and B calling calling E first, and then later we call B, and then B will call D and C. So basically, you have the calling structure like this, and we have a frame pointer that actually is pointing to current call frame, and then each call frame may have static link to the previous call stack in order to get the background reference of the previous variable from the previous call frame. Some language like C language have that calling structure and the variable reference. And we also may have some dynamic link that's not by the calling structure, but by the dynamic reference environment. That's the so-called dynamic scoping. And static link provide the calling structure's reference. So that's the difference between static link and dynamic link. And this link provide different scoping rules, but here we talk about the linking structure because it is used to support those scoping. But here we talk about the fundamental mechanism that support our procedures, not talking about what language is using what scoping. That is belong to the chapter 3, the typing of the programming language. Here we purely talk about the machine. How machine and assembly code is provide a mechanism to support a programming language. But as long as for the programming language is themselves, they have different scoping rule that actually belong to the programming language design. Right here, we actually provide an environment that is more code stack or C assembly code stack or C language related. So we provide a native native control structure for these different languages to be implemented on. Stack, we have a parameter, local variable, temporary bookkeeping information, and heap, mainly for dynamic allocation. So these different stack layout we talk about in this chapter is mainly for the native code or C language or assembly language, that is to support different programming languages. And the stack we talked before, for example, like in Java, it purely on the Java language's code stack. And that code stack actually can be conceptual and operating on Java virtual machine. And for Python, Python's calling environment, linking environment can be on top of C language, and it can be operating on the Python virtual machine as well. Review of code, the stack layout. We have the bookkeeping part. You have the return program counter. You have save register. For example, for each register status, R1, R2, R3 to R16 or something like that. You have a line number. You have save display entries. You have static link to the previous call frame. You have argument and return. You have local variable. You have temporary variables. Now let's look at the calling sequence. Calling sequence is regarding the epilogue and the prologue, how to enter the subroutine and how to exit from the subroutine. So we maintain the consistent programming environment for the program. So calling sequence, the maintenance of stack is responsible for the calling sequence and subroutine prologue. Prologue is for call, is the entering the subroutine, and epilogue, that's the return part. Space is saved by putting as much in the prologue and the epilogue as possible. Time may be saved by putting stuff in the caller instead of the callee. So here are some issues we can discuss. So more information can be known. For example, there might be fewer registers in use at the point of call than are used somewhere in the callee. So we would rather put more stuff on the caller side instead of the callee side. So there are some issues like that. How we partition the register information in the caller and callee. And tasks must be done, including in the prologue, we have the passing parameter, saving the return address, changing the program counter, changing the state counter, the call frame, and then save the registers, change frame pointer to refer to the new frame, and executing an initialization call for new objects. So here, these things must be done before we can enter into a function. So that's why for recursive function, usually the penalty for time is huge, because you need to have this kind of the call and exit portion that take up too much time. In epilogue, we pass in the return parameter on the function values, executing the finalization call for the local objects, the allocation of stack frames, restoring other stored registers, and restoring the program counter, and return the control back to the caller. And here is the structure of a procedure. So basically, we have some call frame, and we have some program, and we actually basically have this different information, and we actually go to call some procedure, and we actually have the callee's frame over here, and caller is over here, and the calling sequence is time domain, not spatial domain. So basically, here is we showing it's actually showing the time domain sequence of save register receiving. So it's like basically like the operation of calling another callee in terms of each step, what should I do? And after you return, what will you do? Restore and run, and then eventually you return, you finish the caller as well. So this actually is a time domain chart instead of spatial domain chart. So calling sequence, the ideal approach is to save those registers that are both live in caller and needed for the purpose of in the callee. So how to determine that intersection setting set so that caller and callee can be balanced? Common strategy is to divide register into caller save and callee save set, and if possible, of equal size. The caller use the callee save the register first, and caller save the register if possible, necessary later. So caller would like to use the callee save registers, so you actually obtaining the registers that actually operated by callee, and then you can utilize your environment result from there. Local variable and arguments are assigned with fixed object. from the stack pointer, so it's easy to get to. And especially for the arguments that is not changing the size, and usually you have a offset for relative addressing in the instruction, you can get certain data. And local variables sometimes it's grossing, the set is grossing, but we also use the offset type of addressing to get to the local variables. And here are the naming convenient name for registers. And we have color safe, temporary, and T registers. We call it T register. These are color safe. Usually color safe have these different temporary or registers. And for Coley, you save some of the temporary may not be overwritten by code procedures. And we have color safe for temporary, reserved for operation system global pointer, Coley safe, stack pointer, frame pointer. These are color safe. So we have different distribution and division of the general purpose bookkeeping information like return value, procedural arguments, and these are actually in lower half of the registers. And then you have the callers register, callees register, and callers register that been for different part of the register file. So here are the distribution. And each time we have the register to be in or swap out, we call it a context switch on the machine. And context switch it takes some time, especially you need to move a large chunk of data from your memory to your CPU. So such a context switch actually will spend some time. And register file can be designed to be in a format called register windows. So each window you have some overlap that you actually pass some variable to as the parameter. So there are some overlap in terms of the coding windows, and those part actually sharing the registers. We call it register windows. So this actually save a time in terms of pushing and popping of the different functional procedures because they have some overlap, and some of the input actually are the output for the previous call frame, and they share the memory, and you don't actually need to pop them or fetch data from memory. That's the register file of register windows. And here it shows you the caller's local and caller's parameter. Actually, caller's frame, caller's frame, to have some overlapping registers. And those registers, we have some operation over here. And usually those are parameters and for the parameter for the caller. And then also it's a parameter for the callee, and callee will use that as local variable as well. So typical calling sequence are here. To maintain this stack layout, the calling sequence might operate as follows. First, the caller save any caller save register whose value will be needed after the call. So that's being saved first. So that actually is the previous frame. You save some data and save the return age. Compute the value of argument, move them into the stack and register. Compute the static link and pass it as extra hidden argument. Use special subroutine code instruction to jump to that subroutine, simultaneously passing return edges. So now we save the return edges and the special link register, something like that. And in this prologue, the callee allocate frame by subtracting appropriate constant from the SP. So basically, you have the return edges saved, argument passed, and then we enter into the prologue for the callee and we enter into current frame. So we save the old frame pointer to the stack. So save pointer to the stack and assign it to appropriate new values. So frame pointer move to a new place. After the subroutine have completed, epilogue will be executed. Move the return value to the register or a reserved location in the stack. Restore code save register if needed. Restore the frame pointer and stack pointer, so we return that to the previous function call frame, and jump back to the return edges. Finally, the caller move the return value to whenever it is needed. Store the caller save register if needed. Calling sequence LLVM. LLVM is low-level virtual machine. So it's on ARM, and LLVM written in C++ is to compile time, link time, runtime, and idle time optimization of program written in arbitrary programming language, originally implemented for C++. So this low-level virtual machine is very popular. Low-level virtual machine is very popular for ARM machine. And by doing that, actually, your C++ language has a low-level virtual machine. You can actually operate your language on top of that virtual machine model. And LLVM now has the action script, Ada, C# command Lisp, Crystal, D, Delphi, and then Fortran, OpenGL, shading language, and here different language, Object-C, Pony, Python, Ruby, Rust, Scala, Swift. So actually, most of the language, Java, bytecode also being supported. So basically, here is a different virtual machine from Java virtual machine. You actually provide you some low-level virtual machine, so you can actually operate on this virtual machine and have the high-level language talking to such a machine. That has different calling sequence from the hardware virtual machine. So calling sequence, a low-level virtual machine. We have prolog callee push necessary register into stack, initialize frame pointer by adding small constant to the step pointer press result in R7, subtract the step pointer, make space for local variable temporaries and the argument build area at top of stack. In epilogue, callee put the return value into R0 to R3 or memory as appropriate. Subtract small constant from R7 and put result in SP, the step pointer. Pop save the register from stack. PC take place LR of LR from the prolog. And actually here you can see that you just set up some proper environment for your function. So we don't actually go into those many details because for those details you actually better I mean when you study more detailed stuff you will actually be able to understand what it is. But right here without the detailed code it's hard to understand what will be needed for these different operations. So calling sequence for this low-level virtual machine, after call, caller move return return value to wherever it is needed. Store, so that is actually our right-hand side value. And then store, caller, save the register lazily over time as their value are needed. All arguments have space in the stack, whether passed in register or not. The subroutine just begins with some of the arguments already cached in the register and the state value in memory. So I would say these calling sequences are complicated, and then just know about those concepts will be good enough. Calling sequence, this is a normal state of affairs, optimizing compiler to keep things in registers whenever possible, flushing into memory only when they run out of registers or when call may attempt to access data through a pointer or from an inner scope. Calling sequence, many parts of the calling sequence prologue and epilogue can be omitted in common cases, particularly leave routines. And then leaving things save times. And then simple leave routine don't use the stack, don't even use memory. And that actually only just operated in the CPU without push and pop. There's an optimization scheme for this LLVM. So as you can see, LLVM is a virtual machine that may be not operated as you imagine. It actually may be optimize your code without even creating the epilogue and prologue for you to run your functional code. That will optimize your environment, and actually it will do different things. So basically we have a assembly coding environment, we have C code stack, C segmentations, and on top of this we may build a low-level virtual machine, Java virtual machine, and our language can be operating on directly to the machine code, or maybe operating on this low-level virtual machine, or maybe operating on Java virtual machine. So those different virtual machines have different calling models, and then have different prologue, epilogue, and different parameter saving schemes. Parameter passing, parameter mode, and call by value. So parameter passing, we have formal parameter, that is the definition of a parameter that has a name, type associated with it. Actual argument is the argument that match that formal parameter. And this actual parameter also called as arguments. So that's method invocation. Java reference data being passed is a passing mode. And then parameter passing mechanism have four basic implementations: value result by copying, reference by aliasing, closure, and name. Four different passing mode. And C language are passed by value, Java passed by value, and then we may have a call by reference. We can have call by name or call by value result. So different parameter passing schemes. And many languages, for example, Ada, C++, Suite, provide value and the reference model for parameter passing. But some languages like C language or Java language, they only have call by value. Parameter passing, pass by value, pass by reference. C++ functions has, for C language, we have post by call by value. Parameter passing by reference can be simulated in C language. So we actually use the pointer, and then we can pass the edges of a variable as pointer, and then its body being updated, so it actually create a call by reference using the pointer, or directly pass by reference in C++. So that in that case, this X become a alias. This X become an alias for the variable that code it. So it's A and B actually, A and X pointing to the same object, and then B and Y pointing to the same object. And inside here, if X got updated, the outside A will also got edited. So that's what we call this call by reference, but actually is actually called by passing the alias into your function. and that x become a input-output variable. So this x become an input-output variable. You can actually pass data into the function through that x. You can actually pass data in, and you can actually also modify the data in the x variable. So value and the reference parameters. So if y is passed to foo by value, then the assignment inside foo has no visible effect. Y is private to the subroutine and the program print to. So if y passed by foo, so here we have x integer, we have procedure y, and then if we pass by value, the 2 is passed to here, so we have a 2 over here, and then that y is updated by 3, but this x is outside, so we actually print 2. But if y is passed by reference, here your x and y are alias. So when y is set to 3, x also set to 3. And when you print x, that become 3. And outside you print again, that's twice. So that's passed by reference. If your y is an alias to x storage and y updated, your x also got updated. Okay, so emulating call by reference in C language. Actually, we talked about this in previous page. You just use a pointer for that purpose. Parameter passing, input parameter and the output parameter. Some language like Ada provide input parameter, output parameter, and in-out parameters. And I think that right now this is not as popular right now in language structure, because we know like your function in C++ language line functions. We have integer f function. We have int alias a and the integer b. So this one is actually input variable, and this one with alias is in-out variable. But if you use the in-out variable purely for output purpose and modify the variable and without passing data, really serious data into the function, then C++ can also implement these 3 modes. So the output variable is actually redundant, a type that is redundant. So pass by sharing, in a language where reference model of variables, ML Ruby, pass by sharing reference is the obvious approach. It is also the only option for portion. You pass the constant, compiler create temporary location to hold it. And if you modify the temporary, nobody care. Call by reference or call by sharing, they are the same in the sense that both change the value of the parameter variables. They are different that parameter in call by reference can point to another object, you can update it, and call by sharing is not. Call by sharing actually is a alias. So call by sharing, call by pass by actually you only pass the reference into there. It still has some subtle differences. Of course, call by reference can be more flexible in a way that it actually you can use the reference as a local variable to be optimized, be updated. Read-only parameter, constant parameter in C language, you can actually declare some variable as constant variable. The parameter receive the value from caller, and at caller the parameter variable work like a local variable. If it is called by value, and it work like a global variable is called by reference. And actually, these different custom parameter in C language, you can think about it, it's just a passing value in, and even if it is a pointer, you cannot modify it. Parameter passing to called by reference, name, and closure. So references in C++, we can create an F alias J that equals I. So I and J now are sharing the same variable. And J with the ampersand sign, actually I would like to read this as alias. So you say alias J is an integer type that assigned by the variable I. So J and I are now alias. So when we pass the variable into a function that has the alias A, alias B, the A and B actually will be associated with different variable from outside callers. And then when we do swap inside here, actually the outside variable that link with the A and B will be changed as well. So C double plus address the problem of no pass by reference by introducing the implicit notion of reference, or let's call it alias, because the sign is ampersand and it's closer to alias. Simplify code with the inline alias. So we have left hand side, we have this body of E is an element assigned by the edges. So then we use the pointer to give reference to the atom aluminum number, atomic number 13 for the record. And right hand side we have alias. So alias is a name for the structure. So for the structure, actually we use the dot as the specifier for the data field. And this one we actually use the dereference sign, arrow sign. So two are equivalent. And we have the operator less that is a insert string to a string. And that is actually one operator in C++ language. Returning a reference from a function. So right here, we actually have this redirection sign A, B, and C. So after you finish the redirection, A is absorbed into C out, and that is another string. And then when B finish, just create a new string as well. And when C finish, we create another string as well. So basically, we actually, by these three statements, we actually create something like this. The result of A and C out is a new string, and that can include B in there and C in there as well. So without reference, left double angle sign and right double angle sign would return a pointer to their strings. R value, a reference, and start string at alias sign string. R value is the right hand side value denote for temporary object that actually you have some value and you provide a temporary value and be assigned to somewhere. So on the left hand side we have L values. So I equals 42, I equals 43. That actually is a assignment of right hand side value to left hand side value. And the address of I assigned to P, that's fine. And then we the foo is an alias of a function. And then foo function equal 42. It's an alias, so foo is a left hand side value. It's assigned by a constant, that's fine. It's the return value for that alias. And then we assign the address for that to P1. Right hand side value, we have foo bar, we have J, we have foo bar, and foo bar returns some value, that's the right hand side value, assigned to J. And then the this alias, the function's alias name assigned to P2. That create error. P2 is a integer. It's not a doesn't take the address of a R value. It doesn't take the address of a function. And then 42 is a R value is okay to be assigned to. R value reference. R value reference allows argument that would normally consider as R value So we can do this. O2, object 2 is a left-hand side value. And this actually is a copy constructor. So we actually copy the object 1 and then create a copy for object 2. This is copy constructor for C language, C++ language. Computer would initialize O2 by calling obj's copy constructor method passing O1 as argument. So it's equivalent to this function that's called copy constructor. The parameter object copy constructor would be constant reference, constant object reference type. The body of the constructor would expect to decide how to initialize O2. If the state is mutable, the constructor will generally allocate and initialize a copy not for string in Java. And then R value reference, we have a alias A or alias of alias A. So here we have move copier, move constructor. So we have object that actually is a constructor, object the alias others. So we have a payload assigned to payload variable, and then others payload as null pointer. That is a implicit move. And then this ampersand of ampersand, it's actually a move constructor. So move constructor R is a reference to a reference. It's a reference to a reference. And move constructor T is a non-temporary constructor whose first parameter is T reference. And for constant type T, for constant type. And then you have T reference volatile, T reference or constant volatile T reference. And either there is no other parameter or the rest of parameter are all default values. And R value reference, we have move constructor. So here we have an A structure. In A structure, we have so many member functions. Our member, when we have trying to move, we actually print that out, and then we call f of A constructor. So A constructor create a object, and that object is of A struct type. So we call that our f function, and f function pass through a object A, and return A, you will return A. So here we actually create an object and then return to A1. And then we move A1, so we move A1 passing the object A1 in there. So we actually will be calling this one. And programmer may know that the value will never be used, passing it as a parameter, but compiler may not know. Programmer can wrap the value in the code to move function. Move generated local, it is in effect a cast. Behavior undefined in the program actually does not contain the subsequent use of O3. So right here we move that. We actually, the A1 being passed to here, and then we do, we call the standard move function. So here we pass OS of O into there. And the move function actually is calling the move function over here. So we pass the test string over there. And then we create a temporary object T. And that actually is a T1. It's an A1. A1 we pass to with that temporary object. And that is actually pass a T. So we for that one actually we create a object with test. And then we pass into this function. And then when we pass into this function, we actually create a move constructor that actually assign test to object A with string test to A2. And then we remove the A1. So that's what we call move constructors. Call by closure. Call by closure. Closure is using a subroutine as a parameter. Closure is a reference to subroutine together with its reference environment. So typical call by closure is the following. We have a function. We have a function access. We have a array right here, over here. And then we have set up integer equals 3. We have function call over here. So we use apply to and pass the function call case access. So that actually we pass a function into there. So function is a access. And that add function is passed to B. And B is passed ASK. Here the integer is B, and then you actually return the sum of M and B. And M is a parameter B being passed. K is assigned with 3 over here. Call by closure. First class subroutine scheme, first class subroutine in ML, subroutine pointer in C, C++. So basically, these different language can pass a function as a parameter to be run into another function. And call by then is used in OGO, but it's no longer needed. So here the comparison for different language and their functions definition information. Lecture 5, Parameter Passing Spatial Parameters. We talked about the call by reference, call by value in the previous lectures. Now, let's look at the spatial purpose parameters. First, conformate arrays. Second, default parameters. 3, named parameters. Fourth, variable numbers of arguments. So the number 4 is for the flexible length. Parameter list of flexible length. And then you can put a conformate array in there and then named parameters in there. Number 1, conformate array. A formal array parameter whose shape is finalized at runtime in a language that usually determines shape at compile time is called a conformate or open array parameter. So basically, you do not specify the size at the compile time, and then it allows the conformate array to be passed as a parameter. And here we have a unidirectional conformate array representation. So basically, there is a maximum count and then size of the elements. and then you actually have size per array element. So basically, there are some information about the array and also with the array elements in a conformed array. Default parameters. This provide the parameter value when you call a function, and then it has a default value. So for Ada, we have type field integer range 0 to the last one, and then we have these procedure, and here we have set the default value to be the integer width, and then default base will have the number base to be 10. And these actually we set up the default value for Ada. And this actually also available in Python language, because in Python we can set some default value in the function. And one common use of default parameter is in IO library routine. And right now, actually, it's not really true about that. Default parameter is quite useful if you don't want to specify your own parameter. Some function, especially in GUI, you can specify certain windows size for width and height. If when you call, you don't have the parameter, you will use some default value for it. That actually is very useful. And any formal parameter that is assigned to the value in its subroutine heading is optional in Ada. In our text.io example, the programmer can call put with 1, 2, 3 or arguments. And if you don't specify, so basically they will use the default value. So if you only provide a parameter, it would be this one, the integer. And then otherwise, if you have second, you will use this one. And if you only have one, you would use the default value. And then if you only have two, the third one will also use the default value. And unless you have three parameter, otherwise the third one will always get the default value. So that's the scheme that Ada has, default or optional parameters. The implementation is straightforward. In any code in which actual parameters are missing, the compiler pretends as if the defaults have been provided. It generates a calling sequence that loads those defaults into registers and push them onto state. So basically, you just need to save a default value when you declare the function. And the compiler, your storage in your method area, you put some parameter for this default value of these parameters. And if there's a function call and you don't have value, this value will be put into the function's parameter list. Argument 2 will be put over there, and 3 will be put over there. If there is no parameter, if you just call f of 1, automatically you will fill it in, and that is in the calling sequence. You will load the default value into there. Named parameter. Named parameter is actually also related to this optional parameter. Named parameter, that means that we can put the value according to the name, so you can provide out of order assignment of the parameters. So you can provide out of order assignment of parameters. And that is good feature because sometimes we don't want to actually keep the by the order. And also if the parameter list is long with the name, actually you can actually provide some parameter like this, so you know that window size, how much would you call it. Otherwise you would, if you just need to follow the order, you will have 2, 400, 200, and then this Helvetic font. Something like that. It actually you will have a long list and you still don't know what parameter have been passed with what kind of value. So this actually is a good feature. In all of our discussion so far, we have been assuming that parameters are positional, and this named parameter can break it, and it will provide you the out of order execution out of the parameter list. And in some language, including Ada, Common Lisp, Fortran 90, Modularity, and Python, this need not to be the case, and these languages allow parameter to be named. And that's one of the reasons I like the Python language. Parameter 4, passing. Parameter passing forward, return value. Function returns. Return statement return the value in a outgoing parameter fashion. So return, you actually have this variable, and then you can return the value back to the right-hand side value, and then it will be assigned to a left-hand side value later. So the syntax in which function indicates the value to be returned vary greatly, so it depends on the language. In Ogo60, Fortran, Pascal, a function specifies its return value by executing a assignment statement whose left-hand side is the name of the function. So there is no return statement. Instead, you use a function's name as the variable to be returned. A function has figured out what to return, but doesn't want to return yet, can always assign the return value to a temporary variable and then return it later. Function returns Ada has something like this. So here RTN. So RTN is the variable you would decide to return, and if you don't return right away, you can actually assign later, and then eventually you return over here. So this RTN variable actually is the declared as a variable so that the function can read it and can modify it, and then eventually you will return it, and it will be processed as a local variable. The return statement must then perform unnecessary copy to move the variable's value to the return location. So there are some overhead, but this actually is quite useful sometimes. Function returns explicitly name the return value in SR. Some languages eliminate the need for a local variable by allowing the result of a function to have a name in its own right. Here, RTN can reside throughout its lifetime in the return location allowed by the caller. So here you actually has the return value, and explicitly name the return value in SR. So SR language, you have a special name for the return value. A similar facility can be found in Alpha, in which every function container is explicitly declare object called result. And this actually is not the most popular way of doing it. Function returns, multi-value return. Python can allow a tuple, multiple tuple for the review. That's for the return. That's actually called multi-variable return. Function return the tuple of values. Many languages place a restriction on the type of object that can be returned from a function. In Argo60, Fortran 77, a function must return a scalar value. The scalar is only one variable. In Pascal and the earlier version of Modular 2, it must return a scalar or pointer. Most imperative languages are more flexible, and Pascal allows the return value of composite type. And composite type is also still not a multi-value return, but the Python and some language allow multiple value return. Exception handling. We finished the parameter passing, and now we look at a special kind of procedure or function or code segment. We call it exception. In early days, we have some operator called assert. So you assert a certain condition. If it doesn't happen, the program will be hold it and then break. So your program will finish. But assert seems not really a good idea because your program will stop, and it actually when your assert statement usually is not okay when you try to ship product. So later we develop people develop this exception handling mechanism. So nowadays, the modern language all have this exception handling routines. So exception handling. What is exception? Exception is a hardware detected runtime error or unusual condition detected by software. When you have index out of bound, you have null pointer, you may have you may raise an exception. So examples are arithmetic overflow, end of file on input, runtime for input data, or user-defined condition, not necessary errors. And user-defined condition is just to use the uh, exception handling mechanism, and you raise some exception of your own definition, and you will go into that to do some spatial processing. So exception handling now may be not handling the errors, but also handling some spatial case that you would like to handle. It's a good format to handle that. So exception handling is a calling structure now. It's a one type of control structure. Exception handling. What is exceptional handler? Call executing when an exception occurs may need different handler for each type of exception. So we actually allow problem to occur and then create exception, and the exception is thrown, and then later we have exception handler. And we will talk about the facility in the language later. Why design in exception handling facility? Allow user to explicitly handle error in a uniform manner. Allow user to handle error without having to check this condition implicitly in the program, else where they might occur. Exception handling is a spatial subroutine code. Workaround to cope with such error without an exception handling mechanism, the programmer has basically three options, none of which is entirely satisfactory. Invent a value that can be used by the caller when the real value could not be returned. Return the explicit status value to the caller, who must inspect it after every call. The status may be written into an extra explicit parameter stored in the global variable, or encoded as otherwise invalid bit pattern of a function's regular return value. Rely on the caller to pass a closure as a function for an exception handling routine that normally routine can call it when it returns to trouble. So here we have several ways to do workaround, but none of them are actually perfect. So you actually invent some spatial value that's treated as a spatial case that actually I don't know. It's not really a good practice, but implicitly return the status code. That's a method that used for OS, but I don't really think that it actually helps a lot because the code sometimes is overridden and it's hard to maintain it through our big software. And then rely on the caller to pass a closure, and that actually is also tedious. Now, here we have an example for unhandled. We have the normal flow of program, and then you may meet a exception. Then you will provide a workaround. We call it exception handling. But right here we have unhandled exception. We have integer of 5 element, but we try to access the fifth index fifth 5 one, but actually that's the 6th element, and actually you will create index out of bound problem, and this is unhandled. And there may be some unchecked overflow, so no exception will be found. So basically, if you have integer 6 divided by 0 and return a C value because it's floating point type, so actually you will see C equal infinity. And then there is no check for this overflow. Handle user-defined exception. So you can actually here in Java, we have good exception handling mechanism. So for the function, you declare that there is a exception to be thrown out. That is the outgoing parameter. So if we try to divide A by B and B equals 0, we raise the exception, and that exception will be actually handled by exception catcher over here as a exception handling routine. So your program go down from here to here and go into the try block and call this division function. And once there is an exception, it will break. This will not be run. It will break and then return to here. You go to here. So the system that out this one will not be run. And because you have some trouble over here, and then you will print out something like this. And then you will print out the value. The value will be the default value 0.0. So this is called try catch block. So your try block is over here. If there's exception, you go to the catch block and return, and try block will join them. That's the flow for the try catch block. So we have an exception as the outgoing parameter. And then when we call the division A and B, and you will see that if B equals 0, then you raise a exception division by 0. That's user-defined object. I'm sorry, that's the actual exception object, but with the user-defined message. And then we continue after the exception handling routine in catch block. So for Java, they are checked and unchecked exception. And usually the unchecked exception will be allowed to run at the runtime. Is usually a runtime exception. Check one, actually, the compiler will enforce it. So there are three types of the error or exception in Java. There's an error type. An error usually is hardware failure or some hard disk failure or something. That's an error. And then there is a runtime exception and the compile time exception. Compile time exception usually is a check exception, and then they want you to check it and provide a handler. And runtime exception is something like null pointer exception, number of format exception, or input index out of bound problem. Those are a runtime exception, and those usually are unchecked exception. And usually those I/O related problem are more like check exception. They want you to check and write down the handling routine over there. Exception handling part 2, try catch finally blocks. So we have a C language, C++ try block. So basically the execution flow is like this. You go to the try block and try out the statement in here. And then if there's an exception, we'll jump to the exception handling routine over here. Otherwise, we will finish the top part and then get out of the after the try catch block. And propagation of an exception out of a coroutine. So if we actually go into the deeply in different level, and that is not handled locally, and you will propagation up to the caller, and the caller have to handle it. If the caller still doesn't handle it, you have to restore. It will be forward to the higher level function that handle it. So defining exception, ADA is something like this, Modularity like this, and the C++ is like this. Exception propagation, we have try catch block, and they may be providing different type of catch block to handle different exception, and all of those exceptions may happen into the try block. So handler on exceptions, we have a function 1 called function 2, function 2 called function 3. But when function 3 happen to have error, it will be provided back to function 2. And if function 2 has handler, you will go to that handler. If not, you will be passed up to function 1. So here is a Java exception publication example. And here we have the method 3 that has exception occurred. And then you would actually method 3, it has a null pointer problem. And you will be thrown back to method 2. And method 2 have no handler. You go back to method 1. Method 1 still have no handler. You go back to the main function, and main function has a catch block to handle it. And if the main function still don't handle it, you will see the exception error message in red ink for Java, similar to C++. So clean up the operation. There is a finally code block, and finally code block is in C#, Java, or Python. They all have the finally block. And Python has tried, but it doesn't use the catch block. It uses the name of the catch block is called except. So you have to know about Python's different structure, but it works similarly to Java. So implementation of exception, we have stacked exception handler. We have multiple exception per handler. So now we have multiple exception, and then this stacked, you will go into like several level. So method that error occur will throw the exception, and then without handler, you will forward the exception to the upper level for the upper level function to handle it. Implementation of exception, we actually will have try block, and then inside the try block, we will detect the error, allow the error to happen, and when the error happen, we will send to catch block to see if there has a matching handler. If no, then you will create the trouble, and you will have the exception being shown, and otherwise it will be handled by the handler. And the handler can be different conditional statements. Coroutine. Coroutine also are subroutines, but coroutine may be conceptually it's a parallel programming mechanism. So conceptually, it's like several routine. You run here, you can call other one and come back to this one. And then later maybe go back to here. And then come back. So here may have function 1 and function 2. And then some of them you call the other one and then come back. And this coexisting function, we call it coroutine. So coroutine is execution context that exist concurrently. So they exist at the same time, but the execution one at a time, but transfer control to each other implicitly. These are called coroutines. Some language have this coroutine feature, and coroutine can be used to implement iterator threads. So thread we'll talk about chapter 13. That will be in our week A lecture. We will talk about concurrent programming with coroutine. Because they are concurrent, coroutine cannot share a single step, so they have different steps. So coroutines are called operative routines. So you may have different function, but A may call B, and B may call C, and C may go back to A, and A, something like that. That is actually some routine that work together as cooperative routines. And how this work out and how this help people to do programming. Some people don't like it and never write something like this. and some people just know how to do programming with this. So like a continued condition, coroutine is represented by a closure, a code address, and the reference environment into which we can jump by means of local goto, and in this case, a special operation known as transfer. So in the old day, we have the goto, and now we have something called transfer. So transfer control to one function. The principal difference between two abstractions is the continued condition is a constant. It does not change once created, while coroutine changes every time it runs. When we transfer from one coroutine to another, the old program counter is saved. The coroutine we are leaving is updated and refactored. Thus, if we perform goto into the same continuation multiple times, each jump will start at precisely the same location. But if we perform transfer into the same coroutine multiple times, excuse me, each jump will take up where the previous one left off. Interleave the coroutine. So that's actually, we have the transfer function, and we will perform like what we say before. It will perform like this. It go to the other one, and it transfer back. So the function that goes from one function to the other function is the transfer. So this one transfer to this function US, and this one transfer the control back to the CFS coroutine. So check file system and update screen. They actually run side by side, and they are interleave the coroutine. Thread and the coroutine. Okay, coroutine are functions running side by side, but they may be within a same thread or same process. And thread has more advanced features, so they just like a different program. So thread, it's easy to build a simple thread package given coroutines. And most programmers would agree, however, that threads are substantially easier to use because they eliminate the need for implicit transfer operations. So thread is now available in Java and Python in different languages. And it actually is similar, sometimes it's similar to the coroutines, and sometimes they are not. And thread is a execution unit, so they need to depend on the scheduler of the operation system. Stack allocation, because they are concurrent, so coroutine cannot share a single stack, but thread can. Thread actually have multiple stack. Each thread has different stack. So coroutine don't share the stack as well. So their subroutine code at the return taken as a whole does not occur in the last in first out format. So it's not sharing the same stack. If each coroutine is declared at the outmost level or lexical nesting, then their stacks are entirely disjoint. The only object they share were global and thus statically allocated. Most operation systems make it easy to allocate one stack and to increase its portion of the virtual address space as necessary during execution. It's usually not easy to allocate arbitrary number of such stacks. Space for coroutine is something of an implementation challenge. So actually, it's not a easy thing to do. So the compiler design need to be very careful to maintain when you have multiple stacks and they run side by side. It's not easy. So it's the stack is completely disjoint. But can you do it in like stack format? We have friend here, friend here, friend here, friend here. It's questionable. So actually using the thread would be easier since you have different process. It's more easier. So coroutine actually not really a lot of language implement the coroutine feature. So state allocation, we have implementation one. Give each coroutine a fixed amount of statically allocated states. So one is just give a fixed amount to certain coroutine. Second, put them in the heap. So heap is dynamic, so you can add or decrease by the programmer whenever you have a call. Number three, mix the fixed and the heap, and allocate stacks in chunks. So here we have the cactus stack. So we have the main program M, and then on top of it, these different stacks sharing the same address space. So we have A function called P function, and main function called B and D, and Q function called C and R. So each branch to the side represent the operation of coroutine A, B, C, D, and the static nesting operands are shown on the right. Static links are shown with arrows. Dynamic links are indicated simply by vertical arrangement. Each routine has call the one above it, so basically anyone above it is a subroutine called by, say S is called by B, D is called by B as well. Transfer from one coroutine to the other. The runtime system must change the program counter, the stack, and the content of the processor register. These changes are encapsulated in the transfer function. So this one is transfer operation. So coroutine is transferred, and then you handle that for those different reference environment. And then later, when you transfer back, you restore it. This is a little bit different from our function code. We had just a prologue and epilogue. So transfer give you different transfer point within a coroutine. So it's more complicated in a way we compare to the traditional functional code. Events. What is event? Event-driven programming is different from this coroutine or regular single-thread processing. An event is in which our running program need to respond, but which occur outside the program at unpredictable time. The most common events are the input or to a GUI system, keystroke, mouse stroke, mouse clicks, and they may also be network operation or I/O activities. In the I/O operations, we assume that a program looking for input will request it explicitly and will wait if it isn't yet available. The sort of synchronous, and the blocking input is generally not acceptable for modern applications. So basically, we have such a programming environment in Windows. So I can hit the escape key. That actually is an event. I scroll, that's an event. Scroll up, that's another event. I can check whatever, or even close this one. It's a lot of different events. And events are sometimes just a object to be processed. Sometimes it's a different thread. So let's look at the event handling routine now. So we have event, and then here we have different environment. In JavaScript case, because it's actually on the web engine on the browser, so actually it's actually just a serial operation, sequential operation. So we have to use a single-threaded event loop to handle all the events to mimic the concurrent programming environment, but it's not really in parallel. In normal website design that even in Java, we have event queue, multiple event queue, and then they will process those applications. In C# process, we have Qt, and Qt use the signal slot mechanism that actually waiting for someone to send you a signal or someone to handle your signal in the slots. And in Java, we also may have the multi-threaded event dispatcher. In that case, each event may have different threads. So we actually, for example, in the Windows system, right here, the PowerPoint, that's one window. And then I have several different windows. This one and this one, I click and drag at different time, but it's not actually controlled by the other one. So it's not a sequential operation. So that can be actually can be in parallel concurrent programming environment. So here is the concept of event handler. Event handler is different from the exception handler, but conceptually is somewhat similar. You actually, but event handler is in concurrent environment, but the exception handler is in sequential situation. So here, say I have an event source. I hit a button, say right now my mouse click, right? And then it sends out an event object, and that event actually is a mouse click. So that event object is an information object that carry the information of your event, and that actually being sent into the event queue, and then event queue wait for a certain time, and it will be processed by the event handler, and then the event handler will react by finding a handler for it. So the handler type, they are action perform, mouse press, mouse release, custom defined, slot function, lambda expression, or callback function. These functions will handle the event, and some of the events are handled because you have different hierarchies. Say here you have HTML, you have body, and they have several division. You have to know that where that this button belong to. So for example, if I click here, this event actually is in this window or this bar. Okay, if I come to here, I click, that belongs to the PowerPoint slides. So the source will determine, put in the information into the event object, and the handler will know, try to determine which part actually is being captured, and then send to the right handler to do it. So there is a capture and a bubbling phase. It captures the event at the button level, but button will bubble up to a certain level to react for the event handler. So the main program go, and then there's a hardware interrupt. You go to the OS kernel to run it, and then you go back to a signal transfer line, and then there's an event handler. And after you finish the event handler, you return, and for the signal transfer line, and then later you return to your main program. Sequential handler, setup handler, a program invoke a library routine, passing as argument the subroutine you want to have invoked when the event occurs. In practice, most handlers need to share data structure with the main program. Thread-based handler. So sometimes the handler is in thread, so you actually send out different threads. So for example, here I click, say I actually sometimes click this, it may incur a different event, but may bring up some different thread. And sometimes, especially when I have this, I click on the window, right? And I actually minimize it, and I pull. This pull function actually create a different browser. That can be a different thread in the window environment. So that's actually a thread-based handler. And that handler actually used to process the thread that I send now. So that's a handler. There's a sequential handler. Sequential handler is used for JavaScript type of scripting language. Thread-based, you have depend on the environment. Many contemporary GUI systems have thread-based handler. Examples include OpenGL, Utility, Toolkit, GLUT. The GNU image manipulation program, the GIMP, Tool GTK, and the Java Swing library, .NET environment, WPF. So here is a event handler in C# language, and then we have the event source of a button, and then we add a event handler to that, an event called pause click, and that event handler is put with this handler over here. So here we have a event source of a button. So here we have a button, and this button actually we add a head listener. So that event is actually for pause button, and then it link with a handler, and that handler is over here. That will help you to handle it. So usually you have to define the event source and event type, and then you also need to know about the event target. Where would it be processed? So the button is event source, and there is a connection or setup for the event handler, and then event handler is written over here. So thread-based handler and event handler in C#, and you actually may allow anonymous delegate. It's different way. Actually, it's just like a anonymous an object or something, an anonymous handler. So this is one way to implement, and the other way is you can use anonymous delegate. And then in Java format, Java environment, you can also have the anonymous event handler. And this delegate is working as anonymous event handler. Thread-based handler in Java you have such have a listener and something like this, and you actually can use the lambda expression as the event handler. That's an anonymous inner class event handler in Java, and you can also have the lambda expression as the event handler. So we can set up a connection by pause listener, and it will be captured by the action performed. And then there is an internet listener. That listener can handle multiple events, and you implement the listener over here to handle multiple events. Okay, thank you. This concludes our discussion in Chapter 9. Chapter 9 gives you the idea of control structure and for different functions. And in Chapter 10, we will work on the object-oriented programming. Okay, thank you. Bye now.